The root. Well, Zach, I'm going to teach, and if you're the only one that hears me, you're the only one that hears me. The roots or the zeros are what this helps you find. The roots or the zeros. Okay? The first batch of examples. When you have a quadratic equation, it can only have x and numbers. Okay? If it has anything other than x or numbers, then it's not a quadratic equation. It can't have radicals. It can't have a variable in the denominator. And it can't have irrational numbers. Okay, guys? So, on this slide, which of these are polynomial functions? Number 1 is a polynomial function. It has no variables in the denominator. It has no unwhole number exponents. That's another no-no. And it has no irrational numbers. So 1 is yes, it is a polynomial. What is the degree? The degree is just the highest exponent. So this would have a degree of 3. What about number 3? What do we think? Why no? Let me go back and relook at that. I was teaching only 2 people, so I was a little off of my vocabulary. And now that I'm thinking about it, you just can't have a square root. I'm pretty sure pi is. You know what? Number 3 in the back of your book in section 2.3. Somebody look at yes or no. I want to say pi is just a number, so it's okay, but I could be wrong. You all could be right. The 1/5 x doesn't give us any problem because the x itself is not in the denominator. That's the same as x over 5, which is perfectly fine. Number 3, back of the book, yay or nay? Thank you, Sam. Even if it is, the degree is going to be 5, 2, 3. 2, 3. Yes or no? Yeah, that's what I thought. Yeah, you just can't have a radical. Pi is fine. It's just a number. So this is yes, and the degree is 5. What about number 5? Why not? Very good. What about number 7? I guess suppose you could, but it didn't ask for that, so for those that are. I guess if this one had a degree, it'd be 3. This one is no, because you cannot have a fractional exponent, which would therefore be a radical. Oh, duh. I remember why the difference between the radical and the... you can't have an x under a radical. You could have a number under a radical, and that would just be fine. That's why I was thinking irrational earlier. See, notice these say no because there's an x under a radical. This would actually be fine if it was just this. But, yeah, you just can't have a variable in the denominator or under a radical. So, 7 is no because a fractional exponent was... And number 9, what do we think? Very good. Polynomial functions are continuous and flowy. That's why we like them. These are polynomials. Smooth, continuous, no sharp corners. These are not polynomials. Polynomials will not have breaks. Polynomials will not have sharp edges. Absolute value, not a polynomial function. All polynomials are going to look like this. Questions about the difference between those two? Identify which ones are and are not polynomials. 11, yes or no? Sarah? You're right. Yes, it is. Latifa, 12, yes or no? Very good. It has a corner. Nathan, 13, yes or no? Close. It can't have a break. It is nice and curved, but it can't have a break in it. So 13 is actually no. And 14, Leslie, yes or no? Very good. Questions about those? Now, this is important. We're going to use this for a long, long time. So I'm going to scoot this over, and we're going to kind of re-talk about this ourselves. You definitely want this in your notes, and this is going to need to go on your note card before the next test. The leading coefficient chart, which is actually I call the end behavior chart. End behavior chart. I'm running out of space. Chart. The end behavior chart. Polynomials can only end 4 ways. Polynomials keep going on forever in both directions, and there's only 4 possible things they can do. They can both be going up in both directions eventually, they can both be going down, or you could have one of each. That's the only possibility. And I'm going to tell you how to know, just by looking at your function, which of those 4 it is. If it's going to be down, up, down, up, or down, down. Doesn't matter what's happening in the middle. This is just the end behavior, meaning as you draw the arrow at the end of your function, which direction do you draw it in? And it's very, very simple. The only things that you have to look for are, is it positive or negative, and what is the degree? Okay? So, degree, think of how I want to do this actually. Yeah, degree, positive or negative, and that will tell you your end behavior. Those 2 will tell you the end behavior of your function. Let's think of one. X squared. Somebody show me with your arms what x squared is going to do on its end. Thank you, Justin. That's perfect. Up, up. Now think about x squared. Is that even or odd degree? Even. X squared. Is that positive or negative? Positive. Very good. If you have a positive function, when I say positive, I mean the leading coefficient. Positive and even gives you an end behavior of up, up. Means your 2 ends are going to be going upwards. EB, end behavior. Running just a little on space on this particular slide. What about negative x squared? What's that going to look like? Very good, Ryan. Negative x squared is an example of an even degree with a negative leading coefficient. I guess I should put leading coefficient, positive or negative right there. And that's going to be down, down, which means eventually on the left and right side, they're both going to be going downward. X cubed is going to look something like this. Going to down, then up. That's going to be a positive odd. If it's positive and odd, then it is down, up. The only one left is what? Odd negative, and that's going to be up, down. Very good. Bless you. Since you can't use graphing calculators, there's going to be more and more graphs on these tests. You're definitely going to need to know your end behavior. Now, there's going to be lots of questions today that ask you for your end behavior. I prefer just to get arrows, but you can put rises, rises, or falls, falls, or if you want to get technical, you can be like, as it goes to the left, it rises. As it goes to the right, it falls. That's fine. I just use arrows. Has everybody got that written down? And do you have a question about what that chart is telling us before we do some examples? Okay. Use the leading coefficient test, which we call the end behavior chart, to determine the end behavior of the graph of the polynomial. What's the degree, odd or even? Positive or negative leading coefficient? Very good. By the way, I don't know if I mentioned this. If I did, then sorry. Leading coefficient is the number being multiplied by your highest power. So odd, positive, what's that going to be? Down, up. Very good. Down, up is your end behavior. Odd is the degree, the highest power, and the leading coefficient, if that's positive or negative. That's what that's from. 21, even or odd? Positive or negative? Therefore, even positive is up, up. Consult thy chart. What about 23? Even negative and thus down, down. I'm just going to be showing you, this whole chapter is about me showing you different tips. That way if I just ask you to sketch a graph, you can do it all the more accurately. Sure. Actually, I think this is one of those sections where it's like the next section is going to ask you something new, but then it's also going to ask you to do that again. So we'll just start with that and work into the new thing. So, It asks us for, let's see, find the zeros. Well, let's just look at 29 real quick. Let's talk about the end behavior of 29. That's odd, positive, and therefore is going to be down, up. Very good. This one is also odd, positive, so down, up. If it had been odd, negative, up, down, etc. Now this one. Find the zeros of each polynomial function and give the multiplicity of each zero. We'll talk about that in a second. State whether the graph crosses the x-axis, touches it, and turns around at each zero. Think about the function. Well, never mind. We're going to get to that in a second, I guess. Today you're going to have to do some factoring. You're going to have to do factoring and or the quadratic equation. However, 25 and 27 are pre-factored, which is awesome because that means you don't have to, you don't have to do that. What's going to make this part equal to 0? Bless you. 5. What's going to make this equal to 0? Now, that negative 4 occurs twice because it's squared. Isn't that the same as x minus 5, x plus 4, x plus 4? So the 3 zeros are negative 4 twice and 5. Now, when it says multiplicity, that means how many times does it occur? Well, if you actually just write it out like this, well, then you've kind of already answered that. The negative 4 happens twice, the 5 happens once. Why is that important? That's important because, do I have a slide dedicated to this? No, I don't. So I'm going to go back and talk about it. That's important because, actually, I'll just show you. The degree is the number of possible times you could cross the axis. Because the degree is essentially how many different possible ways you could break down the x. If you had x to the 7th, then you could have x minus 1, x plus 2, x plus 3, etc. That's just an example. But you could have a maximum of 7 different factors, and therefore a maximum of 7 different times it crosses the axis. Now, what's the end behavior? This is kind of an outside-the-box question. If I were to FOIL all this out, what would my leading term be? If I were to FOIL these two out and then multiply by this, then by this, what would my first term be? 2x cubed. That's right. You FOIL this part out, that would be x squared. Then you multiply by that, and that would be x cubed. Your leading term would be 2x cubed. Now, it doesn't even matter what everything else is right now. Dot, dot, dot. What would my end behavior be? 2x cubed. Very good. It would be down, and it would be up if I were to graph this. Now, according to my roots, this crosses at negative 4 and 5. Negative 4. How could we possibly get back to my end behavior without crossing again? You can't. That's where multiplicity comes into play. If you have a root that occurs an even number of times, 2 in this case, or 4 in some random case, any root that occurs an even number of times is not going to cross your axis. It is going to touch your axis. Therefore, this graph would actually look like this. Just going to touch. And there is a sketch. And you are going to be asked to sketch some today, and yes, you have to do it. But it doesn't take long. I'm not asking for perfection here. This is what I need to see. I see you know you're in behavior. I see you know that it just touches at negative 4 and crosses at 5. That's what I need. So those, you don't have to sketch yet, but that's what it's asking you to do. It's just asking you to list the zeros, state the multiplicity, just write it out like that, and you'll take care of that. And tell whether it touches or crosses. So this negative 4 would be a touch, and 5 would be a cross. Touch, cross. Before we go on to another example, questions about where we're getting any of those conclusions? If it occurs an even number of times, see this occurs twice. If it had occurred 4 times, it would be a touch, or 6, or 8, or whatever, it would be a touch. Anytime it occurs an odd number of times, it's a cross. So like here, what are my zeros? And negative 6 3 times. Now even though this one occurs multiple times, they'll both be crosses because they both occur an odd number of times. And that's really all you have to do for that. So it would be 3, comma, negative 6, negative 6, negative 6, touch, or a cross, cross. They both cross. And that's all you have to write there. 29 and 31, you are going to have to factor. What factors out of 29? Very good. You can take out an x, leaving you with this. Please, 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 please. If you factor an x out of an x, do not just leave that blank. You have to have a 1. If you're a good factorer, then by all means just factor it. If you're not, then you can use the quadratic equation. Negative b plus or minus. I've written this on the board several times. If you still need to write it down, then you just need to write it down in your notes somewhere. So if we were to plug that into the quadratic equation, negative b plus or minus b squared minus 4a, that's a 1. C, also a 1, all over 2a. 4 minus 4, so that's 0. 2 plus or minus 0 over 2. 2 plus 0 is 2. 2 over 2 is 1. 2 minus 0 is 2. 2 over 2 is 1. So, our roots are, what is just an x? What's that going to provide us? What? Yes, sir. Shouldn't that be a negative 2? Yeah, it's already negative. That's what you were asking about? Oh, sure. Okay. Oh, you mean in the as the roots? Oh, 2 is not actually a root at all. Oh, you mean here? These 2 roots? Yes. These are our zeros. What would these be written out as factors? That's right. If we were to rewrite this whole problem, you know, I'm kind of low on space, so I'm going to just cover up that last problem for a second. If I was going to rewrite those 2 roots that we just found as factors, that would be x times x minus 1 times x minus 1. That's how that would have factored if we just factored it. So, our 3 roots are 0, 1, and 1. Anytime you just have an x, that counts as a 0. So 0, 1, and 1. Where's it going to touch? Where's it going to cross? Cross 0, touch 1. Very good. Questions? 29 is the exact same, but how are we going to have to solve it? How are we going to have to solve 29 when we factor it? Rhymes with factor by pooping. Remember this? We talked about this. Factor by grouping. If you have a cube, you're going to have to factor by grouping. Let's work through that one real quick. I can almost hear the questions. Let's look at this one. Factor by grouping. Whenever you bracket off a minus sign, what do you have to do? Change the sign of the last term. That's if you factor out a minus. So, what factors out of the first pair? Leaving me with what? Very good. No. Because you've already changed the sign on the 4. Because it was negative, but when you put the parentheses, it's now positive. So, what factors out of the second one? 4, leaving me again with x plus 7. Anybody remember what I do now? Very good. Does the last one, does this factor at all? Into what? Very good. And then x plus 7. So our 3 roots are negative 7, negative 2, and positive 2. And cross, cross, cross. You need to write that on your paper. Cross, cross, cross. They all cross. Questions? We're going to work a lot more. Yes, ma'am? But they're not the exact same. One's negative, one's positive. It has to be the exact same number multiple times. Good question. Yeah, we're going to work a lot more. In fact, Let me ask you this. What is something, let's look at this particular example. Let's look at this picture. Let's say, what is something, if here's a 0, what's a concrete conclusion I can make about the y values on either side of that 0? Yeah, one's going to be positive, the other's going to be negative. To cross the axis, that has to happen. On either side of it, you have to have a positive and a negative y. That takes us all the way back to our current slide. The intermediate value theorem says, let's say there's a root somewhere between 1 and 2. We don't know what it is. It could be 0.712486559. We could have no way of knowing exactly what it is. But what's a way we can concretely test to see if there's a root between 1 and 2? I'll give you a hint. It's just what we just talked about. What's something you think you'll be able to do? What's that? Well, we know there's a 0. Well, we hope there's a 0 in there. If there is a 0 in there, what should these two y values, if I were to plug these two values into the function, what should their y values be? 0. Negative positive. If there is a 0 between these, then that means that these two, one should be positive, the other should be negative. That way, for them to connect, they had to go through 0. So, all you have to do on this slide, the intermediate value theorem, to test if there's a root between those two numbers, is plug them in. You plug in f of 1, 1 minus 1 minus 1. Plug in f of 2. Now we're hoping that it's what? A positive number. That's 8 minus 2 minus 1. Is there a root between 1 and 2? Yes, because there was a sign change. And that's the only thing we're worried about. We don't care what the numbers are. We just want to see if there's a sign change. Let's try another one. 37. F of negative 3 and f of negative 2. Yikes. Negative 3 is going to be negative 27 plus 9 plus 6 plus 1. Negative 27 plus 16 is negative 11. Plug in negative 2. Yikes. Negative 8 plus 4 plus 4 plus 1. Is that positive 1? Is there a root between those? Yes. If they're both positive or both negative, then it's no. If there's a sign change, it's yes. That's all the intermediate value theorem is. Yes, there will be a test question about one. There will be one of those on your test and homework. Questions about what we're supposed to do there. This is kind of the oddball slide of the day, because I'm about to do a slide that has everything in it except for that. So if you have a question on that, you need to ask it now, because we're not going to hit this again. Last slide, and don't be overwhelmed. Shebang. You have to do the leading coefficient test to find the behavior. You then have to find the x-intercepts. Then you need to find the y-intercept, which is actually the easiest thing on the page. Determine the symmetry is actually also pretty easy, but I'll show you how to do that in a second. And then E says basically just graph. It says you can plot additional points using an XY chart if you want to. I'm not going to require that. But it's essentially E is graph it. Let's do it. Let's just start with 41. So we need to find the end behavior, the roots, the intercepts, the symmetry, and then graph it. Here we go. Step 1. The end behavior. What is my end behavior of this one going to be? Very nice. Odd positive gives you end behavior of down up. Part B. Find the roots. How are we going to have to factor that? By grouping. So that's going to be factoring by grouping. What comes? Oops, that's a 2. What's the coefficient in front of x plus 2? 1. Very good. All we're doing right now is factoring so that we can get those roots. So that'd be x plus 1, x minus 1, x plus 2. So what are my roots going to be? Well, I didn't write these in order, but very good. Negative 1, 1, negative 2. Now, I think it says multiplicity in there. Let's see. State whether it touches or crosses. Here's the thing. Since you have to graph it, I'm going to see if you got that right on your graph. If you want to write the touches or crosses, that's fine if it's going to help you when you graph it. I guess you don't have to because I'm going to see it when you graph it anyway. C, the y-intercept, but all those should cross, right? Because none of them occur more than once. The y-intercept, just like on a line, is just a number without an x. What is that on ours? Negative 2 is the y-intercept. Now, on the ones that are prefactored, you are going to have to multiply it all out. There are shortcuts to that, but I'm not going to go into it. If you see it, good for you. You can take it. If you multiply it all out, the number at the end is your y-intercept. The symmetry. We talked about odd and even functions last week or whenever it was. If you remember, odd functions were symmetrical around the origin. Even functions were symmetrical around the y-axis. And then, of course, neither was neither. So, does this function have all even or all odd exponents? No, there's a mix. It's neither. So this is going to be neither. If they're all odd, it's origin symmetry. If they're all even, it's y-axis symmetry. And that's going to help you when you graph it. And part E is graph. Let's do it. Give myself a little fist. Now, again, you just have to sketch these. You don't even have to put numbers on there. I just need to see the relative spacing. Y-intercept at negative 2. It's supposed to cross at negative 2, negative 1, and positive 1. And the end behavior was down, up. So now all you have to do is connect your dots, more or less. And there's your graph. You went through all your x-intercepts. You went through your y-intercepts. It didn't have any symmetry for you to worry about. And yeah, that covers everything. And there's your behavior. And there's a sketch of that function. Then it should just look, well, we'll do them like that. It'll look symmetrical. When you graph it, it should naturally just take the form of that symmetry. But it'll kind of help you know if you're doing it right. Yes, sir. No. No. No, you don't. Sure. Sure. Okay. Let's do a prefactored one. Let's do 61. Now, it will probably help you. I'm not going to require this because there are ways around it for some, but the more universal way to do it, if you just FOIL all this out and you have both forms, factored and FOILed, then everything will be right there for the plucking. So, we're going to FOIL all this out. I'm going to write the x plus 5, and the first thing I'm going to do is FOIL this part. I'm going to FOIL my x minus 1 squared hoist. I personally think the next easiest step is to multiply through by x plus 5. X cubed. I'm going to take my x by all 3. Take my 5 by all 3. I'll stop and let people catch up. Although the next step is just combining like terms. Now, again, you're not required to do this, but by FOILing it, it'll be easier to see what your degree is, what your leading coefficient is, and what your y-intercept is. The prefactored is nice for finding your roots, because now they're right there in front of you. Combining like terms, it's going to be x cubed minus 2 plus 5, so 3x squared, plus 1 minus 10. All I did that step was combine my like terms. Then we multiply through by the negative 2x cubed, and we're done. Well, we're done with the FOILing. Negative 2x to the 6th minus 6x to the 5th. Remember, when you multiply x's, you just add the exponents. Plus 18x to the 4th minus 10x cubed. Okay, we're ready for our end behavior, our roots, our y-intercept, and our symmetry. First things first, end behavior. Even negative, even exponent, negative coefficient, so it's going to go down, down. Very good. Even, negative. X-intercepts. Well, let's just come all the way back up here to the original. How many zeros do I have? 3. How many 1s do I have? And how many negative 5s do I have? Very good. So that's negative 5 once, 0 3 times, and 1 twice. Now, so which one? What is the one that's going to touch? Yeah, I've answered it. Yeah, 1. What's the y-intercept on this problem? Is there a number without an x? No. Right, so it's just going to be 0. Are all the exponents even or odd? No. Neither. So we're ready to graph. Ready to graph. So our end behavior is down, down. It's going to cross the y-axis at 0. I should change colors. At 0. Let's see, it's going to cross at negative 5. It's going to touch at 1. Here we go. Going up. Cross at 0. Touch at 1. And there's your sketch. That is the whole tamale. Here's the thing, you don't really have to, even if you get symmetry, you don't really necessarily have to, I mean, your graph should naturally look symmetrical when you plot it, but, I mean, I'm not going to count off it's like, hey, that doesn't look symmetrical. But that can help. Here's how that can help you. Let me just look and see if I can find an even or an odd one. Has everybody got that written down? Okay. Let's see. 43 and 45 are even functions, which means whenever I graph them, let's see, this has an end behavior of up, up. This is just a quick, very quick version of this. You find your roots, they're probably going to be like 3 and 0 or something. But what that should tell you is it should just look the same on either side. This is not going to be the sketch of 43. I'm literally just throwing it down. But it's going to look something, you know, like this. It's going to look the same. You should be able to notice it. If you don't, that's fine, but that would have even or y-axis symmetry. Whereas an odd one, an odd function, which looks like 51 would be an odd function, would be something, let's see, it's negative odd, so it would look something like this, you know, where it should look symmetrical. Oops, that's not right. Undo. It should look symmetrical around the origin. See that? That's what something with origin symmetry would look like you're going in the exact opposite direction. You should be able to notice it when you plot everything, but you don't really have to make it look perfect. All right, 41 through 63. I can work any example you want to see. We did 41 and we did 61. I can work any other problem on the board. 50 what? Oh, I can do the odd one. I didn't notice I put the even ones up here. So let me rephrase that. I'll do any odd one on the board. But they should be very similar in their little odd even counterpart. Which one? 55. Let's do it. Ooh, 55 is tricky because it's not fully factored, but it's partially factored. Well, rather than just FOIL it just to have to factor it later, I'm going to go ahead and finish factoring this. That way it's done for me. This part's done. But what does the last part factor into? Very good. Now I'm going to leave that. Now it's fully factored and I can pull out my intercepts later. To FOIL the whole dang thing so that you can pull out everything else, I'm actually going to go back up here. -3. What happens if I FOIL this? Isn't that going to be x squared? This one. This is x squared minus 4. Oh, gross. Here we go. Take the x squared by all three. So that's x to the 4th minus 2x cubed plus x squared. Now I'm going to take the -4 by all three. Minus 4x squared plus 8x minus 4. Combine your like terms. One minus 4. I think that's the only x and the only number. Multiply 3 by your -3. Okay. That's just FOILing. And the only reason we do that is so we can pull out the end behavior, the y-intercept, and the symmetry. Yes, it would. Thank you for catching that. Here we go. First off, what will our end behavior be? I don't know. Somebody's done that. I'm not going to pick somebody. What's my end behavior going to be? What was it? That's right. It is going to be down, down. Even, negative. Down, down. Roots. We'll come all the way back up here for my roots. The second one. What are my roots going to be? 1, 1, 2, -2. 2 1s because it's squared. +2, -2. What's my y-intercept? Very good. 12, the number at the end. Is it all even or all odd? No, it is neither. Most of them will probably be neither. So we're just ready to graph it. Is there a little stuff in here? Anybody else? Feels great. Okay. Here we go. So y-intercept is way up here at 12. It's going to touch at 1, cross at 2, and -2, and my end behavior was down, down. So here we go. Comes across. Yeah. Cross. Oh, this is not going to look very good. Touch, cross, and there you go. Yeah, that's really bad. But nonetheless, it has everything we needed it to. It crossed at 2 and -2, touched at 1, crossed at 12, has my end behavior, and you have a satisfied. Questions about any aspect of these problems? Good question. All you look at is the first term. Even, negative. Even degree, negative leading coefficient. That's it. And then once you have even, negative, you consult your chart and it tells you down, down, up, down, down, up, etc. Other questions? Because x minus 1, couldn't I rewrite this as x minus 1 times x minus 1? Because it's squared. That's why. If it was x minus 1 to the 5th, I'd have 5. Also, you should always The number of these should always match your degree if you did it correctly. The number of these should always match your degree. You shouldn't have any imaginary roots today. We're not to that yet. So,
Is this session being recorded?
I think so.
Are you ready?
Well, I've been sitting here, so yes. You should. Here we go. Here's your assignment.